Welcome back. Dear students, so far we have discussed the formation of partial differential equation, solution of partial differential equation by direct integration, Lagrange's equation and its application, Lagrange's equation and its general solution. Today we will discuss about Charpit's method. Charpit's method is used to find the complete integral for a general first order partial differential equation. So let's see Charpit's method in detail. In this video, we will discuss Charpit's method, working rule for Charpit's method, and some examples and some additional questions for homework. Charpit's method. Let the given partial differential equation of first order and non-linear in PDE f of x, y, z, p, q is equal to 0. Let us take this as equation number 1. Also, here z is the dependent variable. That means z is a function of x and y. So total differential of z, that is denoted by dz, is equal to dou z by dou x into dx plus dou z by dou y into dy. Using the general notations, we can write the total differential dz is equal to p dx plus q dy. So let us take this as equation number 2. Then the auxiliary equations are given by dp divided by dou f by dou x plus p into dou f by dou z is equal to dq divided by dou f by dou y plus q into dou f by dou z is equal to dz divided by minus p into dou f by dou p minus q into dou f by dou q is equal to dx divided by minus dou f by dou p is equal to dy divided by minus dou f by dou q. Let us take this as equation number 3. These equations can also written as dp divided by, instead of dou f by dou x, we can write fx plus p fz is equal to dq divided by fi plus q fz is equal to dz divided by minus p fp minus q fq is equal to dx divided by minus fp is equal to dy divided by minus fq. Let us denote this as equation number 4. Let us see the working rule for Charpit's method. Step 1 is transfer all terms of the given equation to the left hand side and denote the entire expression by f. Step 2, write down the Charpit's auxiliary equations 3 or 4. Using the value of f in step 1, write down the values of dou f by dou x, dou f by dou y, etc. That is fx, fy, etc. occurring in the Charpit's auxiliary equation and substitute these in Charpit's equations 3 and 4. After simplifying step 3, select two proper fractions so that the resulting integral may come out to be the simplest relation involving at least one of p or q. The simplest relation of step 4 is solved along with the given equation to determine p and q. Put these values of p and q in equation 2, that is dz is equal to p dx plus q dy, which on integration gives the complete integral of the given equation. The singular and general integrals can be obtained in the usual manner. So one remark is there, sometimes Charpit's equation give rise to p is equal to a and q is equal to b, where a and b are constants. In such cases, putting p equal to a and q equal to b in the given equation will give the required complete integral. No need to evaluate dz is equal to p dx plus q dy. Only substituting the values p is equal to a and q is equal to b in the given equation will give the required complete integral. Let us discuss some questions. Let us discuss one simple problem. Find a complete integral of z is equal to px plus qy plus p square plus q square. Now solution. Let our first step is, first you have to write down f is equal to 0. So take all the terms to the left hand side and equating to 0, we get f of x, y, z, p comma q is equal to z minus px minus qy minus p square is minus p square minus q square is equal to 0. Equation number 5. In continuation of the above numbering, it is taken as 5. Now, Charpit's, then we have to write down the step 2 is we have to write down the Charpit's auxiliary equations. Charpit's auxiliary equations are dp divided by fx plus p fz is equal to dq divided by fi plus q fz is equal to dz divided by minus p fp minus q fq is equal to dx divided by minus fp equal to dy divided by minus fq. Let us take this as equation number 6. Now, from equation 5, we can find the partial derivatives. Now, fx means partial derivative with respect to x regarding the remaining variables as constant. So, you get when with respect to x, z, derivative of z is 0, derivative of minus px is minus p, derivative of qy, both are constant, so it is 0, derivative of p square 0, derivative of q square 0, so fx is minus p. Now fy, differentiation with respect to y regarding the remaining terms as constant. So you get derivative of z 0, derivative of p with respect px 0, derivative of minus qy is minus q, remaining 0. Fz, differentiation with respect to z. Remaining variables are constant, so we get 1. Fp with respect to p. So here is one term minus px and here we have minus p square. So while differentiating we get minus x minus 2p. And fq, here we have minus qy, here we have minus q square. Differentiating we get minus y minus 2q. Let us take this as equation number 7. Now we have to substitute these values in equation 6. That means we have to substitute all the partial derivatives in the Charpit's auxiliary equation, so that we get dp divided by fx. Fx is minus p plus p into fz. Fz is 1. So p into fz is p minus p plus p becomes 0 equal to dq divided by fy. Fy is minus q plus minus q plus q into fz, q into 1. So minus q plus q is 0. So dq by 0 is equal to, similarly substitute the remaining values, dz divided by p into minus fp. So minus is taken common, so minus into minus becomes plus. So you get p into x plus 2p plus q into y plus 2q is equal to dx divided by x plus 2p is equal to dy divided by y plus 2q. So let us take this as equation number 8. And now we can see that all these fractions are equal. So dp by 0 equal to dq by 0. All these fractions are equal. Say k. Then we can write dp by 0 is equal to k. So we can write dp is equal to 0. So taking the first fraction of 7, we get dp is equal to 0. So that integrating, we get integral dp is equal to, integral dp is p is equal to integral of 0. A constant integral of 0 is, that is integral of 0, that is a constant. So let us take this as a. The constant is taken as a, so we get p is equal to a. Let us choose this as equation number 9. Taking the second fraction of 7, we get dq by 0 is equal to a common value, so that from that we can write dq is equal to 0. So integrating that term, we get q is equal to a constant. Let us take the constant as p. So this is equation number 10. So you get p is equal to a and q is equal to p. Now our using remark, as I told you, we have one remark. If by choosing two proper fractions, if we get p is equal to a and q is equal to p, then the complete integral is obtained by just substituting the values p is equal to a and q is equal to p in the given equation. So putting p equal to a and q is equal to b in the given equation, in equation 5, the required complete integral is given by z is equal to ax plus by plus a square plus b square, where a, b are arbitrary constants.